So we typically need to generate images quickly in new domains. Diffusion models can adapt well, but remain slow to sample in the new domain. So to make these diffusion models fast in these new domains, we traditionally can use two-stage pipelines. For example, we could first distill, then adapt the model, but this would cause over-smooth generations. Alternatively, we could first adapt, then distill the model. However, this would cause overfitting to the target domain. So we propose to unify this distillation and adaptation stages into a single stage pipeline. Our method is able to generate images quickly and preserve diversity and quality in its generation inside the new domain. First, let's look at the improved DMD paper, a state-of-the-art distillation method. In this method, a few-step generator is derived by a distribution matching distillation, learning the distribution of the teacher, plus a GAN loss to increase the realism of the generated images. Our method derives inspiration from improved DMD. We present a student generator for fast sampling on target domain, in this example, images of babies. We do this by presenting two new mechanisms. First, a dual domain DMD for guidance towards the intersection of the source and the target domains, and a multi-head GAN loss to distinguish target domain images from student generations. The training is done by alternating between three steps. First, we update the student. We compute the source DMD, just like the improved DMD paper. Further, we compute a target DMD, which uses a target teacher. By computing a weighted average of these two DMDs, our student is able to fit toward a common area between these two distributions, preserving both the diversity of the source diffusion and also the fidelity of the target diffusion. We also update the student via the GAN generator loss, but we don't use the same GAN loss as in improved DMD paper. We present a multi-head discriminator, which discriminates the image against the target set across different feature scales, reducing overfitting in the case of few-shot target domains. The student is updated via a combination of the dual domain DMD loss and the multi-head GAN generator loss. In the second stage, we update the discriminator and the fake teacher. The discriminator is updated via a multi-head GAN discriminator loss, and the fake teacher is updated via an MSE loss to track the ever-changing outputs of the few-step students. These two models are updated via a weighted average of their losses. At the last stage, in each iteration, we optionally train a target teacher. Note that this stage is fully optional, and for domains that lie inside or remain close to the source teacher's manifold, we can remove this part of our method. We evaluate Uni-DAD on two applications. For unconditional generation, our qualitative analysis shows that, in terms of quality, Uni-DAD remains better or comparable to the state-of-the-art. This is all while requiring less than 4 denoising steps. The quantitative analysis further supports our claims. We often surpass two-stage methods in both quality and diversity, and perform comparably to methods that require significantly more denoising steps. We significantly lower the test cost compared to the non-distilled models. We further require lower training costs compared to the two-stage distilled pipelines. However, the memory usage still remains comparable to the other methods. Parameter efficiency remains for future work. We perform a wide range of ablations to further support our claims. We show that Uni-DAD can also be used as an adaptation method for distilled models, as well as a distillation method for adapted models. We further show that a careful choice of the weight factor in the dual domain DMD loss is needed to adapt well to each domain. We further show that Uni-DAD remains robust to the target size. Specifically, our method performs just as well in the difficult task of one-shot adaptation.
Uni-DAD on subject-driven personalization using stable diffusion v1.5 that is pre-trained on the Layan 5B dataset. We then test it with a Dreambooth benchmark, where the goal is to adapt to a new instance with only 4 to 6 shots and then personalize it. So quantitatively, while only requiring one denoising step, we are able to compete with non-distilled baselines such as Dreambooth and have the best stability trade-off among distilled baselines. Qualitatively, Uni-DAD is able to preserve the subject identity through prompting, recontextualization, accessorization, and property modification. Overall, between the distilled baselines, either they are over-smoothing, over-fitting on the target, or experiencing color fading, while Uni-DAD is able to preserve the quality and the diversity. This was all for Uni-DAD. If you have any question, please feel free to contact us.